sac437 number 2 is a Hall effect problem. We're given a copper strip flattened into the copper wire flattened into the form of a strip. It's got a rectangular cross section. I'm going to look at it from the top. So some copper wire. Part of it is pounded into a strip. Got some current flowing in it. I want to find the directions northward. So I'll label this north, south, east, and west. The current is in this direction. The width of this strip is 8 millimeters. If I look at the strip from, say, the south, view, from south, I can see it in cross section. We're just get a thickness of 1 millimeter, 1 mm, and a width W, where the W is the 8 millimeters. Let's see if that's important. Carries a current 10 amperes due northward. Note that means that the charge carriers, being electrons, are actually moving southward, and it's in a downward directed magnetic field. For which B is 0.5 Tesla. Okay, we're supposed to find the potential difference between the edges. By the right-hand rule, for the cross product of two vectors, V cross B is eastward. And then if we take into account the fact that we're trying to find the force on a negatively charged particle, so Q is negative, that negative sign in the value of Q will flip the vector in addition to changing the units to units of newtons and affecting its magnitude, so that the force is actually westward. So negative charged particles moving southward are what's responsible for this northward current, and the charge carriers themselves are experiencing a westward force. So we're going to get a buildup of negative charge on the west edge of this strip, leaving the right edge of the strip positive. So find the potential difference, make it clear which edge is at the higher potential. The east edge is at the higher potential because we've got positive charge built up there. So east edge and that's part of our answer. So put a box around that. Okay, next Given this information, I is 10 amps. N we found in problem number 1 to be 8 times 10 to the 24th. Conduction electrons, free electrons, charge carriers per meter cubed. There are a lot more electrons than that per meter cubed, but most of them are locked into the copper nucleus. One for each atom is to be considered free, and based on that assumption, we get 8 times 10 to the 28th. Actually, 8th. Check my work there. 8 times 10 to the 28th free electrons per meter cubed. Okay, you've got some formulas on your formula sheet for this, but let's look at it more conceptually rather than just copying down formulas. We're supposed to find the buildup, and what occurs is we get a charge buildup until the electric field caused by these charges exerts a force on the charge carrier that's equal to the force exerted on it by the magnetic field. So the magnetic field force in general, F is equal to QVB. In magnitude in this case is just going to be QVB because V is perpendicular to B. In this picture, B is into the page and V is toward the bottom of the page. There's a 90-degree angle between those two directions. In real life, in real space, B is downward and V is southward. Again, there's a 90-degree angle in between those two, and the cross product is just the product of the magnitudes. In magnitude, when the angle in between the two vectors is 90 degrees. So F is QVB. The magnetic force is that. The electric force is always Q times the strength of the electric field. So this is our balance of sideways or east-west forces on the charged particle in this case. It's the same charged particle in both cases. So the net force on the charged particle is 0. These two forces have to be equal to each other. The Hall potential builds up until that's the case. The delta V over delta X formula that you have on your formula sheet, E in magnitude, like we said, X component is delta V divided by delta X. In this case, the delta X is the width of our strip. We're going from here to here. The potential difference is what we call the Hall potential, and that is the electric field. In the rightward direction, by the way, I should say in the leftward direction, the electric field E is going to extend from east to west, and then the force on the negatively charged particle will be in the opposite direction. Remember, the direction of the force exerted by the electric field on a charged particle is in the same direction as the electric field for a positively charged victim, in the exact opposite direction for a negatively charged victim, which is what we've got here. So these two forces have to balance each other out, and we got the Hall potential is equal to WVB, where V is the velocity of the charged particle in the direction opposite to the direction of the current. It actually drifts in that speed, in that it's moving on the average at a much higher speed, but in random directions due to the thermal motions. We call this V sub D. I'm going to label it V sub D on the diagram. And the force in our case then is going to be Q V sub D times B. And here's our Hall potential. So what we need is the drift velocity and the current. I want to look at our strip here and make sure you get a conceptual or work the relationship between the current and the drift velocity out conceptually as well. What we'll do is consider the amount of charge that's going to pass by a certain boundary, this green boundary right here, in an amount of time delta t. And it's this whole volume of charge will pass through this boundary, and I guess we're going in this direction, so let's make it a red boundary. So the volume of charge shaded in green is to be considered the amount of charge that passes that red boundary. It's all moving in this direction. Oops. All moving in this direction with a velocity v sub d, which is what we're trying to find. We'll consider this to have a length delta x, where the whole mess will move forward, actually southward in this case, in a time delta t, where delta x divided by delta t is the drift velocity. So that much charge moves through the boundary. The volume of that, the amount of charge is going to be the amount of charge per volume times the volume, which will be delta x times the area of this cross section, the area of this face, which is the same as the area of this face right here. I call it A, and that's the amount of charge that will pass by in time delta t. I'll divide both sides by the delta t, and maybe I'll call that delta q, but on this side I've got I. That's the current, and then the charge per volume is what we've calculated and referred to as N. Not quite. The charge per volume is going to be N, which is the number of particles, number of charge carriers per volume, times the amount of charge per carrier, and then this is times A times V. And this will be V sub D. So this delta x by delta t, distance traveled divided by the amount of time that it takes to travel, is what I'm referring to as V sub D. In our case, the charge carriers are electrons, so the amount of charge per charge carrier is just E, the charge, 1.6 times 10 to the minus 19th coulombs, and we've got a relationship between the drift velocity and the current. Depends on the cross-sectional area of the wire, or in this case the strip. Depends on how much charge each particle has, and it depends on the number of particles per volume. We can solve this for V sub D, and this is actually a formula given on your formula sheet. So I've derived it here. Think of that as a review, but you could just copy that down from your formula sheet, unless you're being asked to derive it. One could be asked a problem like that, but and then solve it for the V sub D. The A itself is going to be the thickness, which is 1 millimeter, or T, divided by, or times the width, T times W. So I think I'll express it that way. This is I times N E T W, thickness times width of the cross-sectional wire. So V sub H is W VdB, or W, the Hall potential, is W times V sub D times B itself. It's actually the component of B that's perpendicular to the strip, which in this case would be in the vertical direction, but in this problem the entire magnetic field is perpendicular to the strip. It's all vertical. So this is what we got. The Hall potential is the current divided by NET, where N is the number of charge carriers per volume, number of free electrons per volume, times the charge on one electron, times the thickness of the strip. And then this is the current in the strip, and this is the magnetic field. So we got V sub H is equal to, it's 10 amperes divided by our 8 times 10 to the 28 particles per meter cubed. Particle just counting number, so I'll just call it 1 over meter cubed, and then times the 0.5 Tesla, but we get more in the denominator, 1.6 times 10 to the minus 19th coulombs. Let's work on that denominator some more, times the thickness, which was given as 1 millimeter, 0.001 meters, and then times the B, which is the 0.5 Tesla. Let me take a look at these units first. Got a Tesla, first off, amperes times Tesla, where a Tesla is a Newton per amp meter. And then we've got meters cubed, 1 over meters cubed in the denominator, which is the same thing as meters cubed. Upstairs, we got a meters, downstairs, and then coulombs in the denominator as well. So I got meters squared down there, canceling that out. So I wind up meters cubed divided by meters squared is just meters. The amperes cancel out. A Newton meter is a joule, so we get joules per coulomb, which is volts. Evaluating the number there, I get to 1 sig fig 4 times 10 to the minus 7th volts, or 0.4 microvolts as the Hall potential that develops. So this setup is something we could arrange in the lab. Copper strip about that size, 10 amps is the maximum that we can pump through wire with the power supplies that we've got in your physics lab. 0.5 Tesla, a couple of those neodymium, they're actually neodymium iron boron magnets. They're called neodymium disk magnets. They'll create that big a magnetic field. So we need a very sensitive voltmeter. However, we've got to be able to read down to a fraction of a microvolt, which we'd have to build some amplifiers in order to be able to measure a voltage that small. So not particularly, not immediately practical based on the equipment that we have in the lab to set that up and measure it, because of the very small Hall potential that develops. And we would actually expect that we wouldn't find, we'd find something in the ballpark of that value, but not exactly that value. Again, depending on the purity of the copper that we have, it's expected that our assumption that there's 1 charge carrier per atom is an okay approximation, but not a good approximation. And that's why this calculation is just done to 1 sig fig, and in fact we could measure what the actual Hall potential is and work backwards to calculate the number of charge carriers per volume that actually occur, and based on that you could find out how many electrons per atom behave as free electrons. And it's my understanding that the experiment tends to indicate that the value for good copper, good fairly pure copper, is really about 1.3 charge carriers per atom, where we're basing our entire calculation on the assumption that there's one charge carrier per atom, one free electron per atom, with the rest of them being more strongly bound to the copper nuclei. Alright, let's call it a wrap. This is the Hall potential, 0.4 microvolts, representing the answer, where part of the answer we already expressed and boxed in, with the east edge being at the higher potential. So the east edge is 0.4 microvolts higher in the value of electric potential than the west edge. And that's the answer to SAC 427.